Hey guys, today we're going to talk about parent functions and their transformations. A parent function is the simplest form of that particular function. So for example, if we're looking at a quadratic, the parent function would simply be x squared. If we're looking at the radical function or a square root function, that would just be the square root of x. So the parent function has no other numbers, right? So there's no translations, there's no reflections or dilations, which are our transformations. Now, before we can begin to transform functions, we need to know what the parent functions are and what they look like. On the website, under the homework notifications, I did post a reference sheet that included all of the functions we're going to be working with, which also has pictures of their graphs, so you know what each one looks like. So for example, a quadratic function is a parabola, which looks like a U. The radical function starts at 0, 0, just like every other parent function is centered at 0, 0, and then it just curves outward. The absolute value function looks like a V. The cubic function looks like, like an elongated like squiggle, like an S almost. The cube root function is the same as a cubic function, but it looks sideways, so it would be like that. The rational function is the one that has the asymptotes at your x and y axis, and then you have the curve in the first quadrant and a curve in the third quadrant. The squared rational function, so it's like 1 over x, but it's 1 over x squared, is also where you have your asymptotes at the x-axis and y-axis, but your curves are in the positive quadrants, so quadrant 1 and 2. And we'll investigate these a little carefully as we go through all of the different transformations. Now, for your convenience, I did place reference points next to each function. Now, this doesn't necessarily mean you will always use just these points, as you'll see in examples we're going to do today, but a reference point is basically points that are located on the original function. And I always use the vertex of each function, because it's always located at 0, 0, which is the origin. And then you pick a point to the left and to the right of the vertex. So for example, for the quadratic function, we have the points negative 1, 1 and 1, 1 on either side of the vertex, and etc. So these reference points, the ones in red, are the ones that we're going to use when we're doing our transformations. And this should all seem familiar in a process that we should be familiar with, because in Algebra 2, I know that we did this a lot. So let's start with our most basic transformation, which are translations. A translation simply moves your function around the graph. So either it'll move up and down or left and right. So in each one of these diagrams, I have given you f of x, which is centered at 0, 0, and this is our parent function. If you are adding a number to the outside, think if it's outside, that is your output, meaning it'll affect your y values. If you're adding a number, your function will go up. If you're subtracting a number, it'll go down. Versus when you're adding or subtracting a number inside of the parentheses. So think inside, input, that will affect your x's. If you're adding a number, anything inside the parentheses is going to do the opposite. So if you're adding, instead of us going to the right, it's really moving to the left. And if you're subtracting, instead of moving to the left, you're actually moving the function to the right. So let's look at how we would apply this. Now, translations are the easiest type of transformation, and you can do so by just simply moving the graph around. You don't really have to do much work. You can do it by sight. However, a lot of the graphs that we're going to be working with are going to have multiple types of transformations, and it's just useful to get used to writing the rule of the transformations so that you can do all of that at the same time. Now, how you write the rule would be xy. This represents the points on the parent function. And then you would look at the transformed function. So here my parent function for all of these is the absolute value of x. So we're looking at what is added on to this particular function. In the first one, we see that it's the absolute value of x plus 2. that means that the graph is going to go up 2 units. The 2 is on the outside, so it is affecting your y's, and there's nothing on the inside of the absolute value. That means that your x's do not change. So the rule for the x would be just x. But the rule for the y will be y plus 2, since everything will be shifted up 2. Now the reference points for the absolute value function. You can always go back to the last slide to see what those reference points are. But over here in the bottom, you'll see that I have provided the parent function for each one. So you can see how the translations applied, or rather were applied to the function. If we look at the graph, you see how we have the point at 0, 0, 1, 1, and negative 1, 1. Now, you don't have to just use exclusively these. You can also see that a reference point would be 2, 2, 3, 3, 4, 4, negative 2, 2, negative 3, 3, and negative 4, 4. But to keep things simple, it's just easier to remember negative 1, 1, 0, 0, and 1, 1. So once you have your transformation rule completed, you would take your reference points and plug it into each rule. So the negative 1 is the x, which did not change, and then the y, which is 1, you add 2. So it'll be 1 plus 2, which is 3. We continue plugging in. So we have 0, and then 0 plus 2, which is 2. 1, and then 1 plus 2, which is 3. And now we just plot those points. So we have negative 1, 3, 0, 2, and 1, 3. And you can see that the graph was in fact shifted up 2 units. And this is my transformed graph. For the second one, we have x plus 3 inside of the absolute value. So when we're writing the rule, whatever is inside of your function, you're going to do the opposite. So instead of plus 3, I am going to write x minus 3. Since there's nothing on the outside, our rule for the y is just y. So now we use the same reference points, negative 1, 1, 0, 0, and 1, 1. And when I plug it into the rule, we do negative 1 minus 3, which is negative 4, and the y stays the same. 0 minus 3 is negative 3, and then the y is 0. And finally, 1 minus 3, which is, negative 2, and the y is still 1. So now when we plot those points, we have negative 4, 1, negative 3, 0, and negative 2, 1. And you can see that the graph was shifted to the left 3 units. With our final graph here, we have this that's affecting the x's, so it's going to move to the right 2, and then this that's affecting the y's, so it's going to go down 1. So for my rule, and I don't know if this is helpful, but this is what helps me, I typically like to highlight what is inside of the function and then what is outside of the function so that it's easy for me to see how to write the rule. Whatever is inside, you do the opposite. So instead of x minus 2, I'm going to put x plus 2. And then whatever is on the outside, I think of what I have in the inside as y, and then I just read it from left to right. So this would be y minus 1. So again, we use the same reference points, negative 1, 1, 0, 0, and 1, 1. And I plug it into the rule. For the x's, negative 1 plus 2 is 1, and for the y, 1 minus 1 is 0. For the coordinate 0, 0, we have 0 plus 2, which is 2, and 0 minus 1, which is negative 1. And finally, for 1, 1, 1 plus 2 is 3, and 1 minus 1 is 0. And now I'm going to go ahead and plot those points. So 1, 0, 2, negative 1, and 3, 0. And we can see that the graph was in fact shifted 2 to the right, oops, excuse my squiggle, and 1 down. Moving on to our next transformation are stretches and compressions. And compressions can also be called shrinks. These collectively are your dilations. Now there are technically 4 types of dilations, right? We have vertical stretches, vertical shrinks, horizontal stretches, and horizontal shrinks. And the difference is basically where the number is being multiplied or divided. So transformations all have their own operation, right? We saw that with translations that we were just doing, you're adding or subtracting a number. So if you see addition or subtraction, that means that your graph is simply moving left, right, or up and down. Versus dilations are multiplication and division. So if you have a number that is multiplied, that would be a stretch. If you have a number that is divided, that would be a shrink. And the reasoning for that is when you multiply a number, the number will get bigger, meaning that your graph will stretch. And when you're dividing a number, that means the number will get smaller, and so that will be your shrink. So here are examples. This first image here, we have our parent function, f of x is x squared, which is in black. You see in the blue, we have a 4 on the outside. So that's 4 times x squared. This means that the y values are being multiplied by 4. So this is an example of a vertical stretch. And you can see that it's as if I took my parabola and I pulled at it vertically, making it skinnier. Versus the one in red, we have 1 over 4 x squared. When you have a fraction, fractions are division. So this means that I would take my y values and divide by 4. And if I'm dividing, those y's will get smaller. So that's an example of a vertical shrink. Now, when we move on, if you have a number that is multiplied or divided inside of the parentheses, as you see here, if it's inside, it is affecting your x's, meaning it will be some kind of horizontal dilation. If you're multiplying a number, it will stretch, and if you're dividing a number, it will shrink. But remember, anything that is going on inside of the parentheses, you would do the opposite. So although this particular equation says 1 over 2x, that's as if you were dividing the x's by 2. But you got to do the opposite. So instead of dividing 2, you would actually multiply by 2. And you can see that the graph in red, it's as if I took it sideways and I pulled at it. Think of like an accordion, as if you're pulling open an accordion. So our graph stretches horizontally. So this is the example of a horizontal stretch. Versus the one in blue, you see how in the parentheses it says 2x. Instead of multiplying, remember we got to do the opposite anytime you have something inside of the parentheses. So instead of multiplying, we're going to divide. And if we divide by 2, that means that those x's will get smaller. So it's as if I'm taking that accordion and I'm pulling it back towards the center. So this is an example of a horizontal shrink. So just so we can understand this a little better, here we have a chart, 2 charts that we're going to fill out so that we can remember the differences between stretches and shrinks and horizontals and vertical, etc. If you have some number, so in this case some number like a, which is outside of your function, that represents a vertical stretch or compression, which a compression is the same as a shrink. If that number is larger than 1, meaning 2, 3, 4, 5, whatever, anything larger than 1, that means that we would multiply the y's, and if we multiply, it's going to get bigger. So this is an example of a stretch. Versus if you have a number that is between 0 and 1, that is a fraction, like what we saw in the previous slide. And when you have a fraction on the outside, that means they're going to divide the y's. And if we divide, that number will get smaller. So this would be a vertical shrink. Now when you have a number on the inside, being multiplied or divided. This is a horizontal stretch or shrink. Again, just to reiterate, right? If you have a number on the outside, it affects your y's, which is why it's vertical. If you have a number on the inside, it affects your x's, which is horizontal. If that is a whole, or rather a number larger than 1, so in the example of f of 2x, instead of multiplying 2, you would actually divide the x's by 2. And when you divide, those numbers get smaller. So this is an example of a shrink. And then if you have a fraction on the inside, so let's say f of half x, you're in fact not dividing, but you are multiplying because that is the opposite. So if you're multiplying the x's, that means it's going to get bigger. So this is the stretch. So now let's actually apply this and test it out. For each one of these, we have some kind of dilation. So the first thing that we're going to do is at least recognize what the parent function is. For this one, we have the absolute value of 4x. That means that your parent function is the absolute value of x. Now this 4 is on the inside. And because it's on the inside, that is going to be some kind of horizontal dilation. Remember, we do the opposite. So instead of multiplying 4, we're going to divide 4, making this a shrink. And you always want to write out what is the shrink or stretch of, like by what scale factor. Your scale factor is what you're multiplying or dividing. And in this case, I am dividing 4. So that's a scale factor of 1 over 4. So when you're writing your rule for something like this, we have xy. The rule for the x's, we would do the opposite. So it'll be 1 over 4x. And there's nothing on the outside, so the y will stay the same. Now notice that this means I'm going to divide my x's by 4. If I use the reference points given to you at the beginning, negative 1, 1, 0, 0, and 1, 1 for the absolute value, it's going to be very difficult to plot. Because if you divide 1 by 4, you get 1/4, which is very hard to kind of figure out where that would land on the actual graph. So to make your life a little easier, you can adjust your reference points. So for example, instead of negative 1, 1, I would use negative 4, 4. This is a reference point on my graph. Since it's the absolute value, if I were to look at what the y value was of negative 4, that's as if I were to plug in negative 4 into my absolute value. And the absolute value of negative 4 is 4. I mean, think about what you can see on this graph, right? We have negative 1, 1, negative 2, 2. If I were to keep going, negative 3, 3, and then finally negative 4, 4 would be another point. So we can use that as a reference point. I'm still going to use 0, 0. You always want to use the vertex. And then for the positive side, I would use 4, 4. Again, to make my life easier when it comes to graphing. Now I can plug it into the rule. If I plug in negative 4, 4, negative 4 times 1/4 is the same as negative 4 divided by 4, which is negative 1. And the y does not change, so it stays as 4. 0 divided by anything is 0, and then the y value is 0. And finally, when I plug in 4, 4 divided by 4 is 1, and then the y stays the same as 4. So now I can plot these points. So I go to negative 1, 4, 0, 0, and 1, 4. And this would be my graph. And you can see that this is in fact a vertical stretch. It's as if I took the ends of my absolute value and I pulled at it vertically, making it skinnier. Moving on to b, we have g of x is equal to 1 over 3x squared. Again, this 1 over 3 is on the inside. So this is some kind of horizontal dilation. Instead of dividing 3, I'm supposed to actually multiply by 3. So this is a horizontal stretch of 3. My parent function here, which I forgot to do, would be f of x is equal to x squared, my parabola. And you can see that this is the graph of your parent function. So now we're going to write our rule. So we have xy. The rule for the x's, remember the opposite of dividing 3 would be multiplying 3. And the y will stay the same. And then I use my reference points, -1, 1, 0, 0, and 1, 1. And when I plug it in, I would get the points -3, 1, 0, 0, and 3, 1. And now I can plot these. So I go to -3, 1, 0, 0, and 3, 1. And when I draw this out, this is in fact a horizontal stretch, because it's as if I pulled my parabola horizontally, right, like an accordion, and I stretched it out. I just realized also that for A, I called it a vertical stretch, which actually it is a vertical stretch. Horizontal shrinks are the equivalent of vertical stretches, and horizontal stretches are the equivalent of vertical shrinks. But what makes it different is how it's written in the equation. If it's on the inside, it's going to be a horizontal dilation. And if it's on the outside, it'll be a vertical dilation. But graphically, if I were to look at it, you can call it a vertical stretch and this a vertical shrink as well. All right. For C, my parent function here is is the square root of x, or the radical function. As you can see, we have a number on the outside, meaning it is some kind of vertical dilation. Since I am multiplying 2, that means it is a stretch of 2. So now we're going to write out our rules. We have xy. The x stays the same, but I'm multiplying my y's by 2. So this will be 2y. The reference points for the radical function starts at 0, 0. Then we have 1, 1. And finally 4, 2. And these are the points that I'm going to plug in. When I plug in 0, 0, my point is still 0, 0. When I plug in 1, 1, my point would be 1, 2. And when I plug in 4, 2, my point would be 4, 4. So now we plot. We have 0, 0, 1, 2, and 4, 4. And when I connect the dots, you can see that it is as if I stretched it vertically. It got taller. Last graph, we have g of x is equal to half of x cubed. This means that our parent function is x cubed. Now, because I am dividing by 2 and it is on the outside, this is a vertical shrink. And it's a vertical shrink of 1/2. When you write the rule, the x's have not changed and the y's are half y. Now, when I'm choosing my reference points, even though I'm dividing here, notice that every line represents half. So I'll be able to graph this if I use my regular reference points, which for the cubic function, we have a point at -1, 1, 0, 0, and 1, 1. So once I plug it into my rule, all of those x's have stayed the same, but I'm dividing all of the y's by 2. So my points would be -1, -1/2, 0, 0, and 1, 1/2. So now I can plot. -1 is over here, and -1/2 is just one line down. 0, 0, and 1 1/2. Now look at your dots. Even though they kind of look like a line, you have to remember what your parent function looks like, which is why I gave you these pictures here at first. So you remember that this is a curve. So you have to make sure that you curve your graph so that it matches what your parent function looks like. Moving on to our next transformation. Which are reflections. Reflections are strictly when you see a negative. If you have a negative on the outside of your function, that means that the y values will be changing signs. So it'll be a vertical reflection. Anything on the outside of your function is vertical. And if it is a vertical reflection, that means it is flipping up and down. And if it's flipping up and down, it is flipping over the x-axis. So if the negative is on the outside, it is a reflection on the x-axis. Now, if you have your negative on the inside of your function, so for example, your parent function here is the square root of x. And notice that over here, g of x is the square root of negative x. Notice how the negative is on the inside. This means that it is a horizontal reflection. It is flipping side to side. And if it's flipping side to side, it is flipping over the y-axis. So if the negative is on the inside of the function, then the x's are being affected, and it's going to be flipping horizontally, right, over the y-axis. So let's look at a few examples where not only are we applying negatives, but some other transformations at the same time. So what I like to do, and I'm going to do this again as I did earlier, I'm going to highlight what is inside of my function, and then I'm going to highlight what is outside of my function. So what I mean by inside and outside, we are most familiar with inside if it's inside of a parentheses. But not all of our functions have parentheses to indicate that it's inside. So like for example in b, we just have the square root. You have to look at what your parent function is. If you have only exponents, look for the parentheses. But if it is a square root or a cube root or whatever is inside of that radical is inside. So that is affecting all of your x's. If you have absolute value, anything that is inside of the absolute value affects your x's. Anything inside of, what other function do we have? Let's say a rational function. Whatever is in the denominator with the x, that's affecting your x's. And we'll see examples of that as well. But anyway, so here we have the negative on the inside. So we can expect that this is going to be a reflection across the y-axis since it is inside. So what we got to do is we're going to write our rule since we're doing more than one transformation. Anything that I have in yellow is affecting the x's, and we just read it straight across, right? And you know, like I said, whatever is inside with the x, you have to do the opposite. The only thing that does not change, that's constant, is the negative. If you have a negative, whether it is inside or outside, you keep it. So we're going to keep the negative with the x, and instead of x minus 1, we're going to write x plus 1, because that's the opposite. Then anything outside affects your y's. Think of what is inside as y. So just read straight across. We would have y minus 1. Now we're ready to start plotting. This is my cube root function. That is your parent function. Meaning that the reference points, as you can see from the graph, is -1, -1, 0, 0, and 1, 1. And what I'm going to do is I'm going to plug it into the rule that I got. So if I plug in -1 for the x, we have a negative already, and then times -1 makes it a positive 1, plus 1, 2. Then -1 for the y, minus 1 would be -2. When I plug in 0, 0, -0 is 0, plus 1 is 1, and then 0 minus 1 is -1. And finally, when I plug in 1, 1, that would give us -1 plus 1, which is 0. And then the rule for the y, 1 minus 1, is also 0. So now we're ready to plot. We have the points 2, -2, 1, negative 1, and 0, 0. Remember that this is going to look like a line, but it's not. It is a curve. Okay, and you have to follow the curve of your parent function and make sure that it mirrors that for your new function. Since this flipped over horizontally, right, because it flipped over the y-axis, that means it's going to do that S curve for facing the other way. So remember to curve it. I know it's difficult. And that would be our graph. Now we're going to look at B. Our parent function here is f of x is equal to the square root of x. We have a negative on the outside, meaning it flips over vertically. So it's flipping over the x-axis, meaning it will be upside down. We can expect our graph to go to the right 1 and then up 2. So I'm going to go ahead and write out my rule. The rule for the x's is everything in yellow, so reverse that. So we would have x plus 1. And then everything in pink on the outside is affecting the y's. So we read it left to right, negative y plus 2. My reference points are 0, 0, 1, 1, and 4, 2. And now I'm going to plug in these points into my rules. When I plug in 0, 0, that would give me 1, 2. When I plug in 1, 1, that would give me 2, and then negative 1 plus 2, which is 1. And finally, when I plug in 4, 2, that would give me 5, 0. So now I plot these new points. We have 1, 2, 2, 1, and 5, 0. Notice that it is curving downwards because it flipped over. And this would be my graph. Now let's look at applying many transformations at once. Okay, so now I've taken away the parent function. So you need to know what that parent function is supposed to look like on the graph and what those reference points are. When I look at this equation, since I have that exponent of 2, that means that this is my parent function, x squared. So I can expect my graph to look like a parabola. When I look at what my transformations are, I have that there was a vertical stretch of 2. It went to the right 3 and down 1. So those are all of my transformations. And I'm going to use that to verify that I did my graph correctly. So my rule for the x's, remember anything that is on the inside of the x's, inside with the x's, is affecting the x's, obviously. And anything on the outside is affecting your y's. So I just highlighted my functions already, so it's easy for me to see. Inside, which is the yellow, would be x plus 3. And everything on the outside would read 2y minus 1. The reference points for my quadratic are negative 1, 1, 0, 0, and 1, 1. So now I plug in those points. When you plug in negative 1, 1, you would get 2, 1. When you plug in 0, 0, you get 3, negative 1. And when you plug in 1, 1, you would get 4, 1. So now I'm ready to graph. So we have 2, 1, 3, negative 1, and 4, 1. And remember, this is a parabola, so you got to make sure that you curve it. And this is my graph. And you can see it was definitely moved to the right 3. It went down 1, and it is skinnier, meaning it was stretched vertically. Moving on to my next function, I see that we have absolute value, so that means that my parent function is the absolute value of x. So that means that my graph is going to look like a V. Since a lot of the reference points repeat, like the same reference points for the quadratic are also the reference points for the absolute value. That's why you need to know what the graph looks like. So once you plot those points, you know whether to curve or to form it into the V. So let's write out our rules here. We have xy. Remember, anything inside of the x's, you're going to do the opposite. So instead of multiplying 3, we're going to divide 3, x, and instead of minus 4, we would write plus 4. Now anything on the outside is affecting your y's, so this would be negative y plus 2. So now I'm going to choose the reference points that I'm going to use to graph my absolute value function. Now notice that I'm going to have to divide the x's by 3. So like a previous example, when you're dividing by a number other than something that's easy to graph, like 1/2, I'm going to go ahead and choose reference points that are going to be easily divisible by 3, which would be negative 3, 3 for the left side, 0, 0 always for the vertex, and 3, 3 for the right side. Remember, these reference points are on the graph of your absolute value function, so we can use these to transform. So now I'm going to plug them each into the rule. Negative 3 divided by 3 is negative 1, plus 4 is 3. Then positive 3, right, when I plug it into the rule for the y, would become negative 3 plus 2, which is negative 1. When I plug in 0, 0, that would give me 4, 2. And when I plug in 3, 3, 3 divided by 3 is 1, plus 4 is 5. And then negative 3 plus 2 is negative 1. So these are my new points, and I'm going to go ahead and put that on my graph. So we have 3, negative 1, 4, 2, and 5, negative 1. Now because this is absolute value, remember that this is a V. So I just connect my dots, and there is my absolute value graph. And again, you can use your transformations to verify that you've graphed it correctly. This means it was a reflection over the x-axis, so it is upside down. It was stretched vertically by 3. It went to the right 4 and up 2. So now we're going to kind of work backwards. Now you're going to get the graph of a transformed function, and we want to write its equation. So the first thing you need to be able to do is identify what the parent function is. Now based on the graph, I can tell that this is the function x to the third. So then we have to determine, okay, what happened? What are the transformations that are present? So I put here some cues here for you to look out for. You're going to look where the vertex is. The vertex is usually the middle part of my graph, so where it changes like the curvature. So right here, that is the vertex of my cubic function. When I look at this point, I get the points negative 2, 3. These are my translations. So originally on the parent function, which is over here, remember the parent function is negative 1, 1, negative 1, negative 1, 0, 0, and 1, 1. This is what it originally looks like. I can tell that from vertex to vertex, it moved to the left 2 and up 3. Then we got to check, is there a reflection and is there a dilation? We can see that the graph looked like it flipped over. Whether it flipped over the x-axis or the y-axis in this case does not matter. Because this is an odd function, it's as if you could have, if it flipped over the y-axis, it would look the same. And if it flipped over the x-axis, it'll look the same. So I'm just going to say that it is a reflection over the x-axis. The last part is to check if there are any dilations. And here's a little trick. You're going to pick a point that is either to the left or to the right of the vertex. It does not matter which direction you choose. So let's say on your parent function, I'm going to choose the one on the right side of my vertex. If you compare the vertical and the horizontal distance from the vertex to the next available point is 1. And the vertical distance is also 1. So now if we do the same thing to our transformed graph, you're going to look to either the left side or the right side. Again, it does not matter. So let's say I'm going to choose to look at the left side of my vertex. I'm going to choose the next available point that I see, which is right here at negative 3, 5. If I compare the horizontal with the vertical distance, my horizontal distance is 1, but the vertical distance is 2. This means that there was a vertical stretch of 2, since that distance did increase. And if it increased, it is a stretch. If it decreased, it would have been a shrink. So now that we have all of our transformations, it's time to write it in the form of it's time to write the equation for this graph. Now, here's the general form for any of our functions. A would represent if there was a vertical reflection or dilation. B would represent if there was a horizontal dilation or reflection. H represents if it moved left or right. And K would represent if it moved up or down. You can follow this if you like, and then instead of writing F, you would just use the parent function. Now, I find it easiest to just work my way from the outside in. So what I do is I'm going to open a parentheses. I'm going to put x inside, since this is cubed, and I'm going to put my exponent. Inside, the only horizontal transformation was that it moved to the left 2. So I would write plus 2, since in the equation, remember, it's always the opposite. Then I have this vertical stretch of 2. That means that the number 2 must be on the outside, since it is being multiplied. And there was a reflection over the x-axis that would make a negative. And then additionally, my function also moved up 3, so I would add 3 on the outside. Let's try one more example. Here I notice my function. This is the parent function 1 over x squared. It is the squared rational function. Okay, now what's different about this graph is that there's really no vertex. What we have, however, on these graphs are the vertical and the horizontal asymptotes. And we can see here that the vertical asymptote is located at x is equal to 3, and the horizontal is at y is equal to 2. Now keep in mind what the parent function looks like. The parent function has the asymptotes at 0, at x is equal to 0, which is the y-axis, and at y is equal to 0, which is the x-axis. Then you have the points negative 1, 1, and 1, 1, and then your curves that go through it and never touch those asymptotes. So we can use this to kind of guide what my new function did. Instead of checking to see how the vertex moved, we would check where the asymptotes meet, those points of intersection, how that moved. On the parent function, the asymptotes intersect at 0, 0, just like the vertices of the other functions. In this particular graph, where my asymptotes meet is at 3, negative 2. So this means that my graph moved right 3 and down 2. Now we can tell there is no reflection because it did not flip upside down, and if there was a reflection on the y-axis, it would look the same, so that does not matter. Next, I need to check if there is some kind of dilation. So again, just like the previous example, we can compare the vertex, or in this case where the asymptotes cross, to either point on the left or the right side. So let's just say I'm choosing this point, the one on the right. That horizontal distance is 1 and the vertical distance is 1. And that goes for every parent function. The horizontal and vertical distance from the vertex to the next available point is always 1, 1. So I'm going to check here on my right side of the graph. I'm going to look for my next available point, which is here at 4, 0. And I'm going to see the horizontal and the vertical distance. The horizontal distance is 1, so there was no horizontal dilation. but the vertical distance is 2. This means that there is a vertical stretch of 2. If the distance was 3, then that would be a vertical stretch of 3. If the distance was half, that means it would be a vertical shrink of 1/2. And the same thing for horizontal. So now that I have all of my transformations, I'm ready to write the equation for my graph. So remember, the parent function is 1 over x squared. That means that my equation will be 1 over, and then I'm going to open my parentheses to indicate anything that's affecting my x's. I'm going to put x and then put the exponent on the outside. So what did it do horizontally? It went to the right 3. So I'm going to write minus 3 since we always do the opposite. It went down 2, so I'm going to put plus 2 on the outside. And then there was a vertical stretch of 2, which means that you multiply your function by 2. So I'm just going to put a larger parentheses around my function, and then I'll put 2 on the outside. You can leave your answer like this, but at the same time, if you multiply 2 to this fraction, when you're multiplying fractions, remember you multiply numerator with numerator, denominator with denominator. So this is what that would look like, right? Because any whole number is always over 1. This is the equivalent to 2 times 1, which is 2, over x minus 3 squared times 1, which is just itself. And then don't forget the plus 2. So either one of these answers is acceptable. And that's all of our parent functions and how to transform and write their equations.